Welcome to the screencast about earthquakes. So what are earthquakes? Earthquakes are the shaking or trembling in the earth caused by a sudden release of energy. And that energy is released through the movement of tectonic plates at tectonic plate boundaries. Also at faults, which is basically where just two blocks of crust are moving past one another. They're usually close to a plate boundary, but sometimes they're not. So here's the physical science behind earthquakes. Okay, so let's take a look at a scenario here. This could easily be a scenario along the San Andreas Fault since it's a transform boundary. You can see how we have two plates, moving in opposite directions, right? That is that's a transform boundary. Okay, so let's take a look at that. So first off, you have the crust moving in opposite directions. Energy is stored. It's kind of like a rubber band being stretched. And then all of a sudden, the energy is released. And when that release of energy occurs, you get a trembling or a shaking. So it's called elastic rebound. There's two things as far as where earthquakes occur that you need to know. One is the focus. Now the focus occurs usually, miles underground. Okay, and what happens is the energy transfers up. So that where the earthquake actually starts is called the focus. So that's the focus. But what we normally think of as an earthquake is when it moves up to the surface, and we call that the epicenter. So on the 5 o'clock news, they're talking about an earthquake. They're talking about the epicenter. They're talking about where it actually comes up and hits Earth's surface. Okay, so we've got the epicenter of the quake, and we've got the focus. How do we record or know an earthquake happens besides actually feeling it? Well, we have earthquake recording equipment. It's called a seismometer. So the actual instrument that measures the earthquake, and there's sensors in the ground, and usually it's transmitted to this device right here, the seismometer. Whoopsie daisy. Kind of skipped ahead there. Sorry about that. So that's the actual device that records it, and it's recorded on a seismogram. Seismogram is the actual written record. It looks something similar to what you see here on the screen. Sometimes we may have seen pictures of it being drawn on a roll of paper, but you got the meter, and then you got the gram, and the size comes from Earth's movement. So where do most of the earthquakes occur, and how often? We know earthquakes occur on plate boundaries. So in this picture right here, you've got all of these are known earthquakes, and right along here is actually called the Ring of Fire, where we've got a lot of earthquakes and volcanic activity. So you can see there's quite a few earthquakes along plate boundaries. But then if you look around, you see some that are a little bit away from plate boundaries. So those would be faults. And they're happening pretty much worldwide. You can count on multiple earthquakes each day. And in California, you almost have an earthquake every day. Sometimes you don't feel them. So right here it says 80% of the earthquakes occur along the Ring of Fire. So it's quite an active area. So let's take a look at the seismic waves. This would be on the seismogram. You've got P waves and you got S waves. So let's take a look at this this diagram right here. So right here is where the P wave starts. Okay, so you can see this is the actual P wave, and then right here is where the S wave starts, and the S wave looks like it ends right about here. So you got the P waves, and you got the S waves. P waves, by the way, stand for primary waves, and S waves stand for secondary waves. So it makes sense, right? The P waves arrive first, and then you have the S waves occur. Then later on, you have surface waves. These are the most damaging waves to a lot of buildings. So this is the way that they shake and the way they move on the surface. They really cause a lot of damage. Take a look a little bit more here at P waves and S waves. So the P waves are, as you remember in the lab that we did, it's like the slinky. The waves actually compress. So if you look here, they come in, they actually compress together, kind of like the slinky did, and they move apart, and they compress again, and they move apart. That's how a P wave moves through the Earth. And an S wave moves more differently through the Earth. It's kind of an up and down motion, right? So it causes kind of this little bit of this wavy effect. So P waves are fastest. They travel through solids, liquids, and gases. It's also called a compression wave. The material movement is in the same direction as the wave movement. Secondary waves are slower than P waves, and we saw that on our seismogram. They travel through solids only, and shear waves move material perpendicular to wave movement. And here's a little information on surface waves. Surface waves travel just below or along the ground surface, slower than body waves. The body waves are the P waves and the S waves. They also call those body waves. So the surface waves are slower than the body waves, and we also saw that in the seismogram as well, right? Remember we saw the P waves come in first, then the S waves, and then we saw the surface waves. They're kind of a rolling side-to-side movement, especially damaging to buildings. So, how do we determine the epicenter of an earthquake? What we're going to look at is we're going to look at something called lag time. Okay, and with lag time, you're going to note, and all this is timed on the seismogram. It's all timed, so we have an actual time record, and we know how fast these waves travel. So knowing the time and how fast they travel, we can kind of figure out how far away the earthquake is. So we need to find out lag time first. That's the arrival of the first P wave, and then the time difference between the arrival of the first S wave. So really in between here, okay, in between these two lines right here, that's called lag time. And if we know the lag time, we can tell how far away the seismometer is from the epicenter of the earthquake. Okay. The next thing that we do is we actually draw a circle around where that distance is. So, for example, here they've got a seismic station at New York City, and we know from the lag time that it's so much distance away. So from here to here, so many hundreds of miles. But we don't know exactly where, so that's why we have to have a circle, because it's somewhere along here. But now if we have another recording station at, let's take a look at point B. It looks like it's somewhere in Central California. And we know that distance away is from here to here. We draw another circle, and then we have another location and draw a circle there where they all pinpoint, or I shouldn't say pinpoint, where they all cross, which is right in this area right here. You get a point here, point here, point here. So somewhere within that little triangle right there, that is the epicenter of our earthquake. Oh, it says down here we've got Berkeley, California, great college there. Denver, Colorado, and New York Center, New York City, I should say. Okay, so that's how you triangulate or pinpoint the epicenter of an earthquake. How about size and strength? You always hear it's 6.7 on the, and they're probably saying just a 6.7 earthquake. They're not really saying Richter scale. That's the old method. So if we look up here, you may have heard Richter scale. That's old. We don't use that anymore. We use this modified Mercalli method right here. So the Northridge quake, which was in '94, so a little bit before your birth, but I remember it, seeing all the news clips and so forth. That was a 6.7, so that was a sizable earthquake, and that was on the modified Mercalli intensity scale. So modified Mercalli goes from 1 to 10. Of course, 10 would be a devastating earthquake. I don't know if anything would actually stand after a 10. And it could even go beyond, whereas the Richter scale was a bit more limited and not as accurate. So this is when you hear about an earthquake, 6.7, that's what they're talking about. And each one of these points, 0.7, 0.8, 0.9, that is a huge increase in the earthquake. So we need to kind of keep that in mind here. When you see a point difference, it's actually a sizable increase in intensity. So when we look at this, we're mainly concerned with the destructive power of earthquakes, right? We want to know how it's going to affect us and what actually affects an earthquake, like the buildings and so forth. I mean, what affects the buildings? How does it affect us? Well, it depends on your soil. If you're on top of solid rock, so if we come over here, you've got bedrock. So this is solid rock. If you look carefully at this, they're trying to show less shaking here, more shaking here. If you're on top of bedrock, it's going to be less of a shake. If you have well consolidated, that means fairly well packed soil, it's going to be less of an impact. Poorly packed soil or consolidated sediments, your house is going to shake more. And then if you're on a bay, mud, water saturated, sand like us near the coast, shaking is going to be even more intense. So the type of soil or rock affects an earthquake. So what else would affect us in an earthquake? Well, the type of construction. So on the left, we have a picture of a building after the Haitian earthquake. It was a devastating earthquake, a lot of loss of life, and it was mainly due to the construction of their buildings. Brick and mortar, unreinforced concrete, and those just come tumbling down in an earthquake. Here in California, and actually many homes in the United States, we're using timber frames. So wood bends, and the nails and all the fasteners are made of steel, and steel bends. So this type of structure is actually very good in an earthquake, and it will actually give and move a little without collapsing. So the type of construction will affect you quite a bit in an earthquake, and will affect monetary, how much money it costs to fix your home, and also saves a lot of lives. So you guys, thanks for watching. This concludes our screencast. Make sure that you double check all of your answers on your worksheet that went along with this screencast. And if you just watched this screencast and you forgot to answer the questions on your sheet, that's okay. Just watch it again and make sure you fill that out. That's really going to help you on your next test. So I'll sign off now. See you later, guys. Bye.